Hello, we're going to cover 2.6 part 2, limits at infinity, and we're going to look at the end behavior. So basically what we're doing is we're checking out when x is approaching infinity, what's the function doing? Or when x is approaching negative infinity, what's the function doing? So when we first start off, we're looking at page 18 here, and it says part B, limits at infinity and behavior. So if I look at these graphs, they kind of correspond to what it's saying in part 1, infinite limits at infinity. So if we look at the first one, it says the limit as x is approaching infinity, the function will also be approaching infinity. So if we look at this graph here, and I'm going to trace over what I'm talking about, if I trace over when x is approaching infinity, then what's happening with the function? If we look from left to right, we can see that we're also approaching infinity. And if we take that x and we go backwards or go to negative infinity, so x is getting smaller and smaller and smaller, what's happened to my graph? It's also approaching positive infinity. Okay, so then we're going to look at the next graph. As x is approaching infinity, x can approach negative infinity. So there isn't actually a graph there, but we'd expect the graph to shoot downward, right? As x is approaching negative infinity, f of x approaches negative infinity. So if we look at this graph, this shows that on this side, we're approaching negative infinity. What's going on? Our graph is going downward and getting more and more negative. So that's the negative infinity. Part 2 of B says find limits at infinity and horizontal asymptotes. Okay, so as the limit as x approaches infinity, f of x equals L. L is going to be a constant, like 2 or 3 or whatever. Or we could have the possibility when limit as x approaches negative infinity, the function approaches L, which once again is constant. So the image that we have over here to the right, we can see that there's that dotted line showing a horizontal asymptote. And in this case, the line is y equals 0. In the other example of the graph, we see that this function is approaching 0 again. So the horizontal asymptote would be 0. And we're going to talk about horizontal asymptotes. And I don't know if you remember from the review packet, we had certain criteria that determined whether or not we had a horizontal asymptote, and basically depending on the numerator and denominator's power, it determined whether you had a horizontal asymptote or an oblique asymptote. So we're going to talk about that a little bit later. So there's an actual definition for horizontal asymptotes. If f of x has a finite limit of L, as x approaches infinity or x approaches negative infinity, then the line y equals L is called the horizontal asymptote. So this is another way to find out what the horizontal asymptote is. So once again, if you have x approaching infinity and it's a value like 3 or 4 or whatever, then that would be a horizontal asymptote. And as x approaches negative infinity, if that's a value as well, then you have a horizontal asymptote. So this is another definition besides looking at the numerator and the denominator. So let's look at example number 4. Find the following values and the limits. For part A, given y equals f of x, find the following. For part I, the limit of f of x as x is approaching infinity. So if I look over here to the right, and I think I have this on the next page a little bit more clear. So I'm right here. As x is approaching infinity, what's going on? So x is approaching infinity. So let's go ahead and trace that. What's going on with the function? Well, the function's approaching 0. So we can say that this function is approaching 0. Okay, so I know right now that I have a horizontal asymptote at 0, right? And let's check part I. The limit of f of x as x is approaching negative infinity. All right, so if I'm approaching negative infinity, I'm going this way. So once again, it equals 0. So we know there's a horizontal asymptote at 0. Okay? Write the equation for any horizontal asymptotes. Okay, Well, since we know that it approaches a number and that number is 0, the horizontal asymptote, let me use blue to write this, the horizontal asymptote is 0. All right, so let's look at part B. Part B asks us, given y equals f of x, find the following. For part I, as x is approaching infinity of f of x. Okay, so I look at my graph. Once again, I'm tracing what's going on with the value as x is approaching infinity. Well, if I look here, it looks like it's approaching -2. So I'm going to write down it's approaching -2. And then for part 2, it says the limit as x is approaching -infinity of f of x. Okay, let's see what's going on there. So I'm tracing this, and it looks like we're approaching -1 here. So I'm going to put -1. Write an equation for any horizontal asymptotes. Okay, so my horizontal asymptote, I can say y equals -2, and there's another horizontal asymptote, y equals -1. And by the way, I'm going to go back up to part A for part 3 here, and I'm just going to write y equals 0. Okay, so part C says, given y equals f of x, find the following. For part I, the limit as x is approaching infinity of f of x, and for part 2, the limit as x is approaching -infinity of f of x. All right, so let's check out positive infinity first. If I'm looking here, you know, it looks like I am shooting off and I'm going down to some value, right? And then if I look on the other side, as we're approaching -infinity, you know, it's shooting off this way. So for the positive infinity, it's shooting off to -infinity. And for negative infinity, it's shooting off to positive infinity. You see that? Because we're like constantly going down for positive infinity and constantly going up for as x is approaching -infinity. Okay, so if we look at this, whoops, let me zoom that back down again. If we look at this, it looks like we have an oblique asymptote. So it says write an equation for any horizontal asymptotes. We don't have any of those. However, we do have an oblique asymptote. Okay, what the equation is, I'm not 100% sure because I don't have, you know, data points, and I'm not entirely sure that that line is hitting y equals 4. So it's not asking us for the equation, but however, you can see that it's approaching a line that makes an oblique asymptote. All right, let's check out the next page. Okay, so I am now currently on page 19. And it says limits at infinity and end behavior and algebraic approach. So we look visually, you know, what's happening with these limits. Now we're going to be looking at them in terms of using algebraic techniques. So if I look at this, the basic limit at infinity. So as x is approaching infinity, the limit of c equals c. Remember, c is a constant. So whenever you have just a constant, if you remember from your algebra days, that makes a horizontal line. So for number 1, an example of that would be this, you know, y equals 2. So whenever we take and we have just a constant and we're taking the limit as x approaches infinity, it's just that constant because I haven't moved, right? And then we have the limit as x is approaching -infinity at that constant equals the constant. Okay, that makes sense because now I'm just moving the opposite way on that line. Okay. Number 2 says the limit as x is approaching infinity equals infinity, and the limit as x approaches -infinity of x is -infinity. Okay, so remember just x by itself makes this y equals x, right? And that's this line right here. So if we look at our graph, that makes sense because this x is approaching positive infinity. We're shooting off to positive infinity. And as x approaches -infinity, my line's going down, so that's -infinity. Okay? So if you have the limit of just x, as x is approaching infinity, it's positive infinity. As x is approaching -infinity, it's -infinity. And number 3 is where things get kind of a little bit weird. And just to give you a warning, you have to check these. But the rule says the limit is the limit is x is approaching infinity of 1 over x equals 0. Okay? So if it's just 1 over x, then it's 0. And the limit is x is approaching negative infinity of 1 over x is 0. So let's look at the graph. So this graph corresponds to number 3. As x is approaching positive infinity, we kind of get stuck right before we get to 0, right? So that's why the limit equals 0. And if x is approaching negative infinity, we're getting close to 0 but not hitting it, so that's why it is also 0. So in that case, we have a horizontal asymptote. So if you guys remember, when the numerator's power is smaller than the denominator's, then the horizontal asymptote is 0. Okay? But remember, be careful with that rule because some of these you got to check. Okay? So once again, if the numerator is smaller than the denominator, so if I look at the numerator power of 1, the power is 0, correct? And if we look at the denominator, the power is 1. So 0 is less than 1. Then we have a horizontal asymptote of y equals 0. Okay? All right, so that's just a reminder from algebra and from the review packet. So there's a theorem. If n is greater than 0 in any rational number, and I'm taking the limit as x is approaching infinity of 1 over x raised to the n, I'm getting 1 over a really big number. And whenever you have 1 over a very, very large number, it's approaching 0. Okay? So if I have 1 over 1 million, what's the value? 0. Okay? And if I also can say, if I have the limit as x is approaching negative infinity of 1 over x to the n, I can get 1 over a big number that's either positive or negative depending on your power. But it also is equaling 0. So the rule of the world, I guess, is like if I have 1 over a huge number, it's 0. Okay? But once again, be careful with this definition because there is very rarely, but sometimes it happens when this is not the case. So you just got to be careful with it. But most of the time, it is 0. So let's go ahead and look at this next section. Limits at infinity with rational functions. All right, algebraic techniques, given a limit of infinity over infinity, we have to use the basic limits above, divide the numerator by the denominator by the highest power of x in the denominator. Okay, so what they're telling you in the notes is like if I have infinity over infinity, that's a no-no. Okay, and the reason why it gives you the indiscriminate form, so it's no good. Okay, so when that happens, we have to be clever and do something else. So before I do 5, if I asked you, hey, what is the horizontal asymptote if it has one? And if I look at 5a, I notice that the numerator's power is 1. And it equals the denominator's power, which is also 1, right? Because the highest power we have is x to the first, and the numerator and the denominator. So when that happens, I know I have a horizontal asymptote of 3. Okay? So what's the limit of this? As x is approaching infinity, the answer is going to be 3, right? But let's just do what they said. Because if I plug in infinity, I'm going to get 3 times infinity plus 4. Over infinity minus 2, I get infinity over infinity. That's no good. So when that happens, I got to do something else. And the rule says to take the numerator and divide it by the highest power in the denominator, okay? So I do 3x over x plus 4 over x over x minus 2 over x, okay? The x's will cancel out, so I get a 3 in the numerator. Now, I have 4 over infinity over x divided by x is 1 and 2 over infinity, right? Remember, the rule says When I have 4 over infinity, which is a huge number, that turns to 0. So 4 over infinity becomes 0, 2 over infinity becomes 0, so I'm basically left with 3 over 1, which equals 3. Okay, so our instincts were right. The horizontal asymptote is 3, and as x approaches positive infinity by using algebra shows that it is indeed 3. Okay, let's check this other side. So if I look at this, if I look at the numerator's power, I'm going to see that it's equal to the denominator's power. So therefore, I know I have a horizontal asymptote. If I look at the coefficient, it's just 3, right? It's because I have 3 over 1. But once again, let's go ahead and use the algebra to prove it because it said to do that. So the highest power in the denominator is x. So I get 3x over x plus 4 over x over x minus 2 over x. So it's the same thing I had before, right? So I get 3 plus 4 over negative infinity. Once again, you have 4 over a huge number. It's going to approach 0. And then I get 1 minus 2 over negative infinity. Once again, that approaches 0. So these turn into zeros, and this becomes 3. Okay, so that's 5A, part 1 and 2. And I'm actually going to end this recording and do a part 2 for you so the video is not too long. So that's part 1.